Our next presenter is Mr. Arko Biswas. He is from IIT Kanpur, and topic of his presentation is smart materials driven robotic manipulators. So over to you, Mr. Arko.
So, good evening, everyone. I mean, whoever in India, other parts of the world, maybe there it's not evening or maybe it's morning. However, my topic of presentation is: am I audible, right?
Yes, we can hear.
Okay, my topic of presentation is smart materials driven robotic manipulators. So, first of all, that's my outline of presentation. So first I will introduce what is the need of robots and especially what is the need of smart materials based robots. Then I will try to put some light on what are the useful smart materials that are suitable for use in robotics. Then I will focus on my research area as we are focusing mainly on the shape memory alloys, which is also a smart material. We are trying to use these shape memory alloys to actuate the robotic manipulators. Then I will go on to the methodology, that is the methods through which we want to use these smart materials. Then I will show some plots that I have simulated in especially COMSOL multiphysics environment. Then I will go to the conclusion, that is the what are the decisions or what conclusions we can make from the simulated plots, what are the issues which should be addressed in future. Then we will focus on some already existing manipulators that have been reported throughout the various journals and literatures and try to compare them. And in future, we will try to incorporate and modify those findings of other authors and researchers to develop our own manipulator. So first of all, I want to emphasize that robots and automatic devices have pervaded all the spheres of lives. From it's now ubiquitous, right from the industry, it has pervaded to healthcare, even agriculture, society. All of you have gone through various lectures on cognitive robots, mosquito control robots, etc., etc. So this is the robot has pervaded to the society, to even very remote applications like space, extraterrestrial, extraterrestrial planet exploration, or maybe underwater, below the ocean, below the sea, underwater exploration. In all these spheres, robots have pervaded. Now the problem with such robots is that the conventional robots are generally actuated by electric motors or maybe hydraulic and pneumatic actuators. Electric motors is a very heavy device. Also for hydraulic and pneumatic devices, we need the compressor or blower. Also in case of hydraulic, we need the fluid to store. So all these things render the whole robotic system very heavy, and it becomes very cumbersome to apply in smaller and remote applications, as I had mentioned. In healthcare applications, many robots are needed which must be small in size, which must be compact. Or also in the remote applications, right, underwater or the space exploration, the robots must be lightweight and they should be of small size. So it becomes difficult to use these electric motors and hydraulic pneumatic actuators in the robots that are supposed to be used such applications. To overcome these issues, so lighter and more compact actuators need to be developed for the robots that are meant for the aforesaid applications like space, underwater exploration, or maybe agriculture or healthcare applications. So in these directions, we found that the smart materials appear to be a good candidate owing to this high power to weight ratio, in some cases force to weight ratio or torque to weight ratio is also of interest, and the smaller size, the compact size. Next slide, I will introduce what smart materials denote. So smart materials are a typical category of materials which respond to some specific external stimuli, maybe heat, maybe light, maybe magnetic field, maybe electric field, etc. Some specific external stimuli with significant and predictable changes. In robotics, most often these changes correspond to significant and predictable deformations. In robotics, what we want, we need to actuate the robotic joints using these smart materials. So what happens, these smart materials are placed at the joints of the robots, especially, and when they deform on application of the appropriate stimuli, the joint is actuated and along with the robot link also moves, which lead to the, so in robotics, most often these changes correspond to the significant and predictable deformations, which lead to the actuation of the robotic joints. So now, what are the smart materials that are very popular nowadays? First of all, shape memory alloys, and followed by shape memory polymers. Apart from, there are electroactive polymers which actuate on application of electric field or electric voltage. Apart from that, there are several smart materials like rheological fluids, electro-rheological fluid, magneto-rheological fluids, or maybe photosensitive, thermosensitive, light sensitive polymers are there. So these are the very smart materials that can be applied, that appear to be good candidates for the application of robots involving smart materials, especially owing to their large deformation and relatively simple excitation process. So I was telling that shape memory alloy, shape memory polymers, these are the very smart materials which appear to be good options, good candidates for the applications just I have mentioned, owing to their large deformations and relatively simple excitation process, because these can be simply excited just by applying a voltage or maybe using light or heat, etc. Maybe magnetic field. These involve very simple excitation process. These materials also exhibit high force to weight ratio, or maybe in some case high torque to weight ratio, which render the whole robotic system lightweight and smaller, that is more compact. Now, right now we are mainly focusing on the shape memory alloy. So I want to introduce a bit on what shape memory alloy is. Shape memory alloys are mainly characterized by their ability to restore original shape and size, original configuration after undergoing a significant, substantial deformation. Actually, shape memory alloys exhibit two effects which are very popular. The one is the shape memory effect, which we will be using to develop the robotic manipulator, and another is pseudo-elastic or super-elastic effect. This shape memory effect is a thermomechanical effect. That means it involves both thermal load, that is heating, as well as mechanical load, that is stressing. It is characterized by large deformation under mechanical load, followed by restoration of original configuration during heating. That is, when the material, the shape, the shape memory effect is the effect when the shape memory alloy is deformed by applying a huge stress, and it appears that it has permanently deformed. And now the force, even after the force is withdrawn, even after the stress is withdrawn, it retains most of the deformation, most of the strain. Now, if this shape memory alloy is heated beyond a particular critical temperature, what happens? This shape memory alloy is found to restore its original shape and size, its original configuration upon heating. So it involves both heating, that is thermal load, as well as stressing, that is mechanical load, and hence the name thermomechanical effect. So this is actually the shape memory effect. Another effect is pseudo-elastic or super-elastic effect. It is only mechanical effect, that is, it involves only mechanical loading. What happens here is the shape memory alloy is, when shape memory alloy is stressed with a mechanical load, it it get deformed. It gets deformed after when we start withdrawing the mechanical load. The shape memory alloy is found to restore its original configuration at a much lower load, and that causes a hysteresis, that is a different path. It following a different path, it restores its original configuration. So this is called pseudo-elastic effect. So these two beautiful, these two peculiar effects are due to the fact that SMAs consist of two phases, and one phase transforms into another, and that's why shape memory alloy shows these two peculiar effects. Shape memory alloys consist of mainly martensite and austenite crystalline states. Actually, the transformation between the two phases accounts for these unique characteristics of the SMAs. You can see the austenite is a high temperature phase, whereas the martensite is a low temperature phase. So when SMA is prepared, it remains in a high temperature austenite phase, and it remains in a body centered cubic structure that is shown by the red atoms here. Now, when it is cooled without any application of strains, what happened? It transformed into a twined martensite structures. You see this twined martensite. So can you see my cursor moving? Hello?
Yes.
Hello, can you see my cursor moving?
Yes, we can see.
Yes. So look at these
Yes,
atoms.
we can see. Arko.
Yes, look at these atoms. So these above atoms and the below atoms, they are kind of mirror image of one another. So these are called twined martensites. Similarly, for this line, the above and below rows of atoms are mirror images of each other. Similarly, if you consider each line of atom, the atoms above and below it represent the mirror images. So these are called the twined martensite structure. Twined martensite structure. So when the austenite transforms into this twined martensite structure, no deformation occurs. Then this happens just by cooling. Now if these twined martensite structures are stressed, so it undergoes straining process, then the martensite crystals undergoes detwining, and they arrange themselves in a strain preferred planes. That is the direction in which the strain are applied. These atoms will arrange themselves in that directions. So this is the green atoms represent detwined martensite phase, which is obtained by straining this twined martensite phase. Now when this martensite phase detwines, it undergoes a large permanent strain. So even when the applied stress is withdrawn, the detwined martensite retains most of the strain. Now, if this detwined martensite phase is heated beyond the critical temperature, it will again come to the austenite body-centered cubic phase, and it will again regain its original configuration. That is the red atoms. So in this way, the shape memory effect works. Actually, the shape memory alloy regains its original configuration. Here is the temperature martensite phase versus temperature curve. Actually, the martensite volume fraction, that is in a given sample of SMA, the martensite is present is denoted by xi. Xi denotes the martensite volume fraction of a given SMA sample. Okay, so xi is plotted along y-axis and temperature is plotted along x-axis. So start from here, from the austenite phase. Austenite phase is generally the high temperature phase, and it is the parent phase. It is the parent phase. When it is cooled, following the red line, when temperature is decreasing, at this temperature ms, the martensite starts to form, and if you go on decreasing the temperature, the martensite will the whole of the austenite present in the sample will transform into martensite at this corresponding to this temperature. Martensite finished. Hello?
I apologize to interrupt you. your time is almost over, so can you speed up your presentation?
Okay, sure.
Thank you.
Okay, so this is the Martinshide phase versus temperature curve. So here so for the interest of time, I will quickly go through these slides. So what we are thinking that when we will use the shape memory effect of SMA to drive the manipulators, and we are interested in SMA wares to use to actuate the robotic joints. So we have used the COMSOL multiphysics environment to simulate the SMA wares in complex loading conditions. That is when the SMA wares are subjected to both stress and thermal load, that is temperature or heating. And we have done stationary and time dependent studies both, but from the realistic point of view, the time dependent studies are more realistic from the application point of view, because when it will be applied in a robotic joint, it may be subjected to both stress and temperature. um, in COMSOL, so SMA wire has been exposed to electrical, that is, we used electrical joule heating to heat up the SMA wires, and we also applied mechanical stress. The variation of various parameters, namely like the Martin side volume fraction, the temperature, etc., as well as stress strain. The variation of these parameters with time have been plotted. Actually, here we have used an nitinol wire which is subjected to 10 megapascal constant stress and a 10 volt applied voltage, and we have got this kind of plot: the stress versus time, the strain versus time. This is resembles this, and the displacement also. Displacement and strain both are almost same. Actually, this point corresponds to the change of phase. I will come to that. Martin volume fraction is changing this to this, that is, all the martensite is transformed into austenite form in this region, and the temperature is varying in this way. Now we have simulated another nitinol where here the load is increased linearly from 0 to 10 megapascal, and the voltage is remained constant. We got this kind of plot of stress versus time. See, that is not fully linear. There are some plateaus like peaks here. So the strains, we have got these kinds of strain and displacement curve, and the Martenside volume fraction versus time graph. This one, the temperature curve is more or less same. So the conclusion is that that even in the presence of joule heating, in the presence of complex loaded condition, the phase change can be induced using joule heating. But the displacement that was found here is very small on the micron scale, maybe due to the force applied, due to the stress applied. So suitable geometric arrangements need to be developed to enhance the displacement, to magnify the displacement. Quick phase change and rapid rise in temperature have been observed because no control over the heating, because we could not control the voltage applied. So what we are thinking that we may control the electric current flowing through the SMA, or by adjusting the convecting heat transfer coefficient by controlling the speed of the blower blowing air. By this we can control the heating and phase change of the SMA wires. After addressing these issues by implementing some control methods of electric current or maybe convective heat transfer, after addressing these issues, the SMA wires will be integrated with the proposed robotic manipulator, and experiments will be carried out to see its performance and compare the results with those of the SMA based manipulators already reported in various literature. Next, I have given some examples from the literatures, that is how some authors have done work. This is a work done by some author, Guzman and et al. So they have used an agonist and antagonist mechanism to actuate this robotic manipulator. These are the SMA1, this is the SMA2. One is agonist and the antagonistic, and another is antagonistic to actuate this robotic arm. So there is another example where this is a segmented robotic manipulator. So using this, there are three circumferentially arranged SMA wares. So these is a so by activating these SMA wares differently, various kinds of motions like bending, that is in this way shown here, shortening or elongation can be achieved with these manipulations. The central compression spring here keeps the segment straight, at the same time gives enough flexibility to bend freely. Another is this SMA wire. Actually, these SMA actuators are attached to the joints as shown in the CAD model. Here in the CAD model, you can see this is an SMA wire, and also this is an SMA wire. These two links 2 and 3 are provided with IMUs, that is inertial measurement units. These inertial measurement units are supposed to estimate the angular position, that is the orientation of the links, orientation of the respective links, and this will provide signals to the closed loop controller. So these novel ideas we were trying to report it in the literatures, we are trying to incorporate them, and also we want to modify these novel ideas and to while developing our manipulator, so that it can handle a larger payloads, following which the developed manipulator will be integrated to the agricultural robot being developed in our SMSS laboratory. Okay, that's what I wanted to present.
Yeah. Thank you very much, Arko, for your nice presentation. So from audience, if you have any question, kindly you can ask. Okay, I will have a quick question. Which model you have used for your simulation? Which mathematical model?
It is mainly Lagoda's model, DC Lagod SMA, right?
Yes.
SMA, right? Lagoda's model, the cosine.
Okay. And you have said one solution for cooling the SMA wire using blowers.
Yes.
Right. So
yes.
My question is like the main purpose of using SMA is to reduce the weight of actuation, right? To reduce the weight of actuator. Can you hear me?
Yes. Okay. Reduce the weight. I got your question. Because
yes, so if you add
fans,
one
it will
more
add
blower, yes, it will add to the actuation. So do you think like it will be a
heavy lightweight?
Yes.
That's why we are thinking of mainly the first one, the controlling the electric current. But what happens, as because the Indian atmosphere, because it's very hot atmosphere, and these robotic manipulators are supposed to be integrated with agricultural robot. In the field, the temperature may go very higher. So at that time, we may not have other options rather than introducing a blower, because only by controlling the electric current we cannot control the heating. That's why
I got that point, but it will it will fail the purpose, right? Because the purpose is to build up a lighter actuator.
Yes.
Right. So maybe you can think of some other option, maybe later. Okay. Okay. That's all from my side. I think Aniruddha have something to ask. So Aniruddha, please.
Yeah. So thank you, Arko, for that presentation. I just have one question, like from your studies and simulation, for what kind of payload can we design this manipulator? Like, what can be the payload capacity of this manipulator that SMA can drive?
That depends on the size of the SMA wires. That is, we are using 0.51 millimeter diameter of SMA wires. So if we increase this kind of SMA wires can handle a payload maybe not very high, but maybe within 300 gram. It's
But
up to this.
my question is like, can you get that value of payload from your simulation study? Like, is there a way to
Okay.
determine it?
So, yes, we used only 0.51 millimeter diameter SMA wires. So if we increase the diameter, that is the size of the SMA wire, maybe we will be getting higher payloads, but I have to work on it. I have to work on it. That is for which diameter SMA wires, what amount of, I mean, how much weight we can lift. That is, we can do it. We can find it from our simulation. We have to work on it.
Okay, thank you, Arko.
Okay, welcome all of you.